I want to thank Larry Milstein over there for the invitation to be here tonight to address this august body. We've had a wonderful meal, and I hope to be able to add some spice, as it were, to the evening by entertaining you, I hope, with the beauty and promise of molecular nanotechnology. So this means that we are going to visit on a small scale, starting with, if not atoms, with small molecules, at actually below the nanometer level, sub-nanometer, and moving up through tens and hundreds and maybe thousands and more of nanometers, with again, an emphasis on beauty and promise that, for me, come together in this area just as much as do love and marriage. Let me start by wearing my science on my sleeve. I'm a chemist, and I'm proud to be and have been associated with chemistry for almost half a century now. Why was I attracted to chemistry? It wasn't by smells and bangs and that kind of thing, maybe by colors. It was the opportunity to have a career where one could be creative. And Marcel Berthelot, in Paris in 1860, was to put his stamp on chemistry as it creates its object. And in comparison, he said, this creative quality, resembling that of art itself, distinguishes it, i.e. chemistry, essentially from natural, I presume the parlance of these days, physics, and historical, let's say, biological sciences. The latter have an object given in advance and independent of the will and action of the scientist. And the point he was making is that amongst the sciences, chemistry offers one the opportunity to dabble in art. And so, before we move on, let me just, many people have written about creativity. I actually use a text by the near neighbor, the University of Chicago, to the south of where I am at Northwestern, to make some comments about the flow and psychology of discovery and invention. Creative persons all love what they do. It's not the hope of achieving fame or making money that drives them. Rather, it's the opportunity to do the work that they enjoy. Curiosity and drive are in many ways the yin and yang that need to be combined in order to achieve something new. The first require openness to outside stimuli, the second inner focus. The first is playful. Let's just think of the late Steve Jobs and how he went to a class in calligraphy when he was a student. Playful. The second, serious. The first deals with objects and ideas for their own sake. The second is competitive and achievement-oriented. Both are required for creativity to be actualized. The right milieu is important in more ways than one. It can affect the production of novelty as well as its acceptance. Therefore, it's not surprising that creative individuals tend to gravitate towards centers of vital activity where work has the chance of succeeding. The great centers of learning and commerce have always acted as magnets for ambitious individuals who want to leave their mark on culture. Aside from science, I always cite the fact that in the period of, say, 1900 to 1910, Paris was a place to which artists and sculptors writers of every complexion would flock. I guess in modern times we would look to the east and the west coast, and obviously to the Midwest of the United States for centers of excellence in science and technology. Creativity is rarely the product of a single moment. I really believe this very strongly, particularly in relation to chemistry. Perhaps more often it's the result of a lifetime. This reflects the fact that a lot of creativity is associated with incremental advances in the science. Creative individuals usually are forced to invent the jobs that they will be doing all through their lives. Creative individuals don't have careers, they create them. And so I'm always at a loss when a graduate student comes into my office and says, what should I do in terms of mapping out my career? And I just think of this comment here by this author, and I think maybe I've not been posed the right question. Okay, but then let's move on, because Berthelot was making this comparison with art. But what is art? Well, according to Wikipedia, it's the process or product of deliberately arranging elements in a way to affect senses or emotions. This is quite a suitable definition for chemistry. The process or product of deliberately arranging elements. So the essence of creativity is inherent, if you like, to both disciplines. Whence the beauty of chemistry? Let's hear what Nobel laureate Roald Hoffmann up at Cornell and Pierre Laszlo in Belgium have to say. Our discipline is a curious mix of empirical observation and abstract reasoning. This is not unlike music, but it parts chemistry from the pure rigor of mathematics. Tracing molecular beauty back to the Platonic tradition. So to Plato, the most beautiful bodies in the whole realm of bodies were the tiny polyhedra. Here they are, all 5 of them: cube, tetrahedron, octahedron, icosahedron, dodecahedron. And they're now deemed the Platonic solids. And the first 4 of them make up the 4 elements of earth, fire, air, and water, leaving the dodecahedron to constitute the ether. So chemical aesthetics, in the words of this philosopher of science, Joachim Schumer, modern chemistry is exactly the art that provides creative access to what Plato considered the realm of the most beautiful bodies. Therefore, it is no surprise that chemists put their creative activity also in the service of beauty. And so, what I've been trying to say with these introductory slides is that I was attracted to chemistry by, first of all, its beauty, not by smells or bangs or explosions. What about chemistry in relation to molecular nanotechnology? Well, yes, we can see beauty in materials, the colors of pigments and crystals, the shape of the crystals, the beauty in the structure of molecules themselves. And simple molecules have taken up the Platonic type of structures, cubane, dodecahedron, and beyond to these so-called C60 or Buckminster-Fullerene molecules, where simply beautiful and beautifully simple is a good description of that molecular world. Molecular nanotechnology, on the other hand, is yet another way to address beauty in chemistry, because here we have miniaturization coming into play. We have the whole concept of doing chemistry beyond the molecule. We can look at tonight the paradigm shift in molecular representations that has occurred as a result of the advent of molecular nanotechnology and its influence on chemistry. So we'll be seeing how graphical representations and cartoons become very much the order of the day and give us a link into the world of the artist. So, these so-called catenanes and retaxanes. Again, we go back to Wikipedia to tell us what a catenane is. A catenane is a mechanically interlocked molecular, and I emphasize molecular. This is the smallest entity that is represented at the level of a compound, the molecular architecture consisting of 2 or more interlocked macrocycles. You may have seen in the prelude the emergence of olympiadine, a molecule that we made some almost 20 years ago now, which I won't talk about tonight, but you can play on the symbolism that is out there, that is in everybody's mind. And remember, London will attract the Olympic Games this very year. A retaxane is a mechanically interlocked molecular architecture consisting of a dumbbell-shaped component. So this is the component with these green balls at the end with this red rod surrounded by a blue ring, so that the dumbbell-shaped component is threaded through 1 or more macrocycles, just a fancy way of describing this ring here. And doesn't this type of imagery bring to mind the abacus? And I actually have graduate students from China in my research group at Northwestern who actually learned to count in this day and age on this contraption. So mechanically interlocked molecules, which I will sometimes refer to as MIMS for short, are going to be our bread and butter this evening. But before we go there, I just want to point out this whole concept of interlocking is pervading our lives: scissors, bicycles, chains, knots, nuts and bolts. And here, at aged about 6 months, is my first grandson, also James Fraser. I can tell him he's James Fraser II, holding in his left hand here essentially a 4 retaxane. He's got this dumbbell. If you want to say his hand is a ring, we can push it up to a 5 retaxane. So we meet these constructs at a very, very early age. I wish I had the image of my twin grandchildren playing this very Christmas and New Year period with interlocked rings, but it was not possible to include that. Here, staying with the catenane, are images that show the friendship that now exists between England and Australia, despite the fact that Australia was used as a place for sending the criminals from England for many years. Here in Portsmouth, you see the catenane displayed in this sculpture, and here is the equivalent one in Sydney. And expanded version of the version that is on display in Sydney in Australia. But you always find that in this imagery, you can go back a long time, and who knows when all this started, because one of my graduate students came back from China a couple of years ago after he was married and said, we discovered in our local museum here this catenane that dates back over some 700 years in terms of its imagery. So this is me introducing the mechanical bond. Since there's no so-called covalent, or let's just say straightforward chemical bond between the components, that's the blue and the red component there, or the green plus red and the blue component over there, in alternatively, or respectively, a catenane and a retaxane, the linkage has been called a mechanical bond. It got its expression, well, over 50, almost 60 years ago. Where do the names come from? Well, catenane comes from the Latin catena for chain. Retaxane comes from a combination of rota, wheel, and axis for axle in Latin. And usually accompanying this type of molecular construct is the idea of molecular knots. And so I'm going to mention these knots, the simplest of which is called a Treflow knot. Now, if I were to pick out the scientists who have been the forerunners, effectively, in the field, I would have to pick out Gottfried Schill, now probably in his early 80s, spent most of his career in Freiburg in Germany. He never became more than a C3 professor, but he wrote a book in 1971, or published a book in 1971, which I think could be looked upon as one of the Bibles in the subject, at least from the point of view of posing the problems that chemists and biologists and physicists might wish to address using these types of molecular constructs. So staying with the Treflow knot, it's an interesting species because it's what we call topologically non-trivial. It's just one component. You can trace it around here. The bonds of a classical chemical nature are attached one to the other. But overall, the expression of the topology gives it handedness, so that you could look upon this one as being a left hand and this being a right-handed type of molecular expression. And so we say that irrespective of the chemical constitution, this molecule is topologically capable of giving a left-handed or a right-handed expression to the world. It's unconditionally topologically chiral. And one of the people, a very good friend over all of my career, who has effectively promoted this area of knots as well as catenanes and retaxanes, is Jean-Pierre Sauvage at the University of Strasbourg. And he has helped to take the making of such molecules from being just a statistical and hoped-for event. Schill brought in what are called covalently directed methods, and then Jean-Pierre Sauvage, using metal templates, brought in so-called template-directed synthesis, and he edited a book in the late 90s in which we were contributors. So, chemists are not finished yet. There are a lot of knots, and one of my thesis tonight is probably one that will surprise other scientists in the audience. Chemistry is by a long, long way the youngest science in the universe at the moment. I will come back to that theme later on, but just look from the point of view of topology what we face, and you will get a feel during my talk for how far we've managed to get. Well, here is where we've been with the trefoil knot. This is where we're going next. It's a little bit of a jump. It's no longer a knot. It involves 3 rings, and it's been called the Borromean link. And how does it get its name? Well, it comes from the family crest of the Borromeo family. I probably shouldn't have Italy there, because Italy only dates from about 1860 or 1850. But from that Renaissance part of what became Italy back in the 1450s. And you find this set of 3 rings on the crest of the Borromean family. Now, I have it in good authority from a scientist of long-standing friendship, Luigi Fabrizi, that in this period of time, when the pilgrims were making their way from Florence to Rome, it was too big a journey to do in one day, and so they would stop off at an inn, and these were the Bon Romeos, the good people going to Rome. And the inn became known as the Bon Romeo or the Borromeo Inn. And the family, being the innkeepers, made a lot of money. And if you make a lot of money in Italy, even in those times, you head north to Milan. And in those days, the Duke of Milan was a bit of a warmonger, and he needed money to be able to fight his wars, and he had lots of land. And so the Borromeo family became massive landowners in Tuscany and those regions of Italy. And so if you go there today as a tourist and drive around Lake Maggiore and places like that, you will find these family crests adorned with the family crest of the 3 rings. But there are no firsts in any of these activities. About the same time, you have Sandro Botticelli and his painting of Pallas in the Center, displayed in the Uffizi Gallery in Florence, showing the imagery on the dress of Pallas, as it turns out here. But we can push the time scale back even further if you're prepared to take on triangular formats of this particular topology. Here you have the Vikings in the 9th century coming up with Odin's triangle walnut, as it's known, on this tombstone. It's a symbol that's been used through many, many cultures over many, many centuries, millennia, to bring 3 concepts together: the Father, the Son, and the Holy Spirit in Christian iconography. And here you see it in a nice setting in the St. Vitus Cathedral in Prague, photographed by one of the ex-postdoctoral scholars in the group. Not just the preserve of Western culture, but you can find it in Japanese culture as well. And on a more light-hearted note, after World War II, I think it was, the London Underground system produced this map, and if you zero in on Charing Cross, as it's called, then you will find that the imagery of the Borromean rings is present there. And then back here in the United States, Ballantine's beer has purity, body, and flavor all joined together in the same symbolism. If you're a mathematician, it's the Venn diagram that you use. So if I take any color here and relate it to the other color, say I take the green, I pass over, then under, then over and under the red, the blue, the red, the blue, alternately. Plus, minus, plus, minus. If you're a chemist, though, you like to see things in 3 dimensions. And so you create this orthogonal type of representation. And it is here that I make the point that this is a unique way to bring together these 3 rings, because If I decide to cleave the red ring, you can see that the blue and the green one can float away from each other without being cleaved. The same holds for cleaving the green ring. The red and the blue can float away from each other. And finally, cleave the blue ring, and the red and the green can leave each other. So if you're going to put together this assembly of free rings using mechanical bonding, you think, first of all, that it might be appropriate to make one ring at a time. Let's make the red ring, let's make the blue ring. And we pursued this way of thinking, as did others in the world at the same time. This was an input by Chu, as we know him, now professor, a full professor in the National Taiwan University in Taipei. And then think of feeding the green one through, but to get the topology right, so that at the end of the day, you get this wonderful construct. It all looks wonderful on paper. And in fact, as Chu showed, and other people have shown, this is actually quite easy. This is actually devilishly difficult. And this is really then academic. No one's done it yet. So you're at this point where, in a pursuit of just, can we make this? Well, it's like climbing Mount Everest, I guess. You have failure after failure. And this is when you turn to this two-liner by, or one-liner by Noel Coward. The secret of success is the capacity to survive failure. You don't give up. And so let's look at, again, the planar Venn diagram, the orthogonal arrangement. And one day, a couple of my research students who made the passage from Birmingham in England to Los Angeles in California, it was quite a big transition for them. It was like going to the moon. And the two of them got together and started to dream up if they could use some metals at these points there and just put some bends in these rings, they might be able to do this not one step at a time, but all at once. And I wouldn't be showing you the imagery here if this didn't turn out to be the case, and to be the case in a stunning sort of way. So it ended up that, yes, they used 6 metals, and they turned out to be zinc. You can do it with many others, but the first one was with zinc. They had teeth that had 3, as it were, teeth to them, and we call these the endo ligands. These are the ones that are pointing in. And then there are the exo with 2 teeth to them ligands. And the 2 are these sort of waistline components there, and the frees are the ones at the periphery of the blue, the red, and the green. And I'm going to, of course, show you that the chemical constitution of blue and red and green is the same. And what they also felt was necessary was to be able to do this so that everything was occurring in a making and breaking sense at the same time. So it seems a bit counterintuitive. You want to make something, but you're going to be breaking it at the same time. And the reason that you do this is to search out on a very big landscape the lowest energy component. And they had done a lot of computing and so forth, and come up with the belief that if they took a compound shown in the west and the east here, which we could buy from Aldrich Chemicals, so that wasn't difficult, one which involved a few steps of chemical synthesis of a traditional type, but that could be done. They argued that if they put these together, they would have the 2 inward-pointing ligands, as they're called, with 3 teeth, these 3 nitrogens in the east and the west, and 2 in the north and south with 2 outward-pointing ligands. And what's more, they would arrange it so that the reaction takes place between this so-called amino group and this aldehyde, so that water is lost, and the formation of a carbon-nitrogen double bond occurs 4 times over, and this carbon-nitrogen double bond is called an imine. And this is a reversible process. The 2 people involved are Stuart Cantrell and Anthony Pease. Anthony Pease is, I think, now making a lot of money in the City of London. But I want to tell you something about Stuart Cantrell, because one of my themes of this evening talk is getting from the academic world people trained to do rather out-of-the-box and important jobs in science. So Stuart hailed from the middle of England, very bright. He had a first-class honours degree under his belt at Birmingham, an MPhil, before we moved to California, where he obtained his PhD. He then went to Caltech and did a postdoctoral period with Nobel laureate Bob Grubbs, and then returned for 2 or 3 years to help me while I was a director of the California Nanosystems Institute. But the most important thing I want to point out is that I had my arm twisted to be an associate editor of something called Organic Letters. And I gave, as part of Stuart's job, a third of his time to being the editorial assistant. Well, that third of the time ended up being everything that I would have done. I didn't do anything effectively. He just lapped this up and did a wonderful job. And this is where he found out what he wanted to do in life. So he then returned to the UK and joined Nature Nanotechnology in London, and after a couple of years made a bid to be the editor-in-chief of the newly to be launched Nature Chemistry, and got the job. I saw him last night. Nature Chemistry, now on basis of impact factors, forget about review journals, is now #1 in the world. This young boy is pretty influential in the world of publishing of chemistry and indeed molecular nanotechnology. Science Watch have just interviewed him, if any of you are interested of taking up a recent commentary on where he sees the importance of this journal, which had its first issue in April of 2009. But it didn't turn out that Anthony or Stuart were the people who brought the molecular Borromean rings into being. Turned out to be a couple of Canadians, Kelly Cheekjack and Andrea Peters. Now, man and wife, they're at the GE Corporation. Kelly, after only a few years there, is being nominated internally for many awards in quite different areas from what I'm talking about. Oh, here are their 2 twins. They're now just over a year old. Jolly holding the Borromean rings here, and Eston, the male of the 2, trying to pull them apart. Anyway, back to the chemistry. This is what Kelly was effectively very good at, just staying with conditions, conditions, and conditions, until one day he came up with crystals. And this is always the dream of a chemist, to see structure expressed at a larger level than the molecular level. And we were happy. And that happiness prevailed, and then it started to wane, because we're not expert crystallographers, and so we were seeking help from many crystallography labs around the world, and the time was going by, and we weren't getting results. And then, let me just interject something personal here. One of the reasons I went to Los Angeles in 1997 was that my wife was suffering from breast cancer. Here she is. And it was a 12-year battle with that insidious disease, starting in 1992, and you can see she died in 2004. And it was towards the end of 2003 that I learned from her oncologist that her disease had made its way up into her brain. And I returned from that rather devastating day in the clinic in the morning, and opened my email up, and there was the structure of the Borromean rings, courtesy of Jerry Atwood, a good friend down in the University of Missouri, Columbia, and his postdoctoral assistant, Gareth Cave. So here we had this nanoparticle at 2.5 nanometers with these 6 zincs and the free rings here in a symmetry that had been predicted by Anthony Pease. The zincs constitute, if you like, a Platonic solid, the silver octahedron, and the oxygens that line the inside of this cavity are cube octahedron. And here is Kelly's sort of artistic rendering of this nanoparticle, if you like. I just want to point out that it has a considerable amount of space in the middle, and this may be topical. We have some ex-postdoctoral scholars from the group now looking at the porosity of these compounds for the take-up of gases such as hydrogen and carbon dioxide. This is Kelly's impression. Remember I told you about the making of this molecule. Now, this is very much an artist's impression, but the important thing is, as it's being made, it's also being broken up. And of course, it is simplified, this whole process. Some of the things that would be made wouldn't be the rings that are constituted here. They would be too big or they'd be too small. But at the end of the day, we end up with a 99% yield, effectively, of these Borromean rings. To all intents and purposes, it's what the chemists call quantitative. So here we are, all together. If we should, as a company, feel inclined after my talk, you can get together and freeze and see if you can constitute with your hands clasped in this way the Borromean embrace. So there's Kelly Stewart and myself in such an embrace. So this was a feeling of great pleasure, and so at this stage I go to Robert Burns, the Scottish bard. But pleasures are like poppy spread, you seize the flower, its bloom is shed. Or like the snow falls in the river, a moment white, then melts forever. Or like the borealis race, that flit ere you can point their place. Or like the rainbow's lovely form, evanishing amid the storm. One of the gentlemen that was very much in cahoots with your founding fathers, I should say, in that very important period in American history. So, I challenge you, if you Google Borromean rings tonight, you will get at least 40,000 hits. They are everywhere in art, heraldry, logos, science, and sculpture. But let me just, to change the tempo a little, take you on a trip around the Borromea College in Pavia. I had the opportunity to go around this college in June of 2007 with a graduate student, Carrie Mayer, and we were conducted around by Giorgio Melorio, himself a chemist and vice rector of the college, and I will hopefully get some music. The interesting thing about that trip was probably only 10% of the assemblies of free rings on the part of the artists had the right topology. It was quite interesting. So this is a graduate student that went round with me, and I just want to, again, in featuring the input of the young people, point out that Carrie also added something to our understanding by one day just using different conditions. So we'd usually, as you saw, I didn't point it out, but it was on the slide, had a mixture of diethyl ether and methanol to crystallize the Borromean rings. So she also added another alcohol, N-propanol, one day and got a completely different set of crystals. And this is quite remarkable because it turns out that from these same components, remember, none of these free rings are mutually in pairs interlocked. She got another structure with only 2 rings that are doubly interlocked. And this is called the Solomon knot. And it really does underline the fact that this whole activity of crystallization is not a science, it's an art. And so solvent does matter, and you have this equilibrium set up, and if you use these conditions solvent-wise, you get the Borromean rings. If you use those conditions, you get the Solomon knot. And the Solomon knot, unlike the Borromean ring, comes as a left-handed and a right-handed molecule. Here is an artist that I met up with in Massachusetts, Mike Thompson, a physicist by training, who has given artistic expression in this triptych to the soup, as we call it, that constitutes giving us the Solomon knot on the one hand, or the Borromean ring on the other, from this soup in the middle. Here's another little ditty from, this time, Luigi Mandolini in Italy. He was born in Pesaro in Italy, and so he drew my attention when I gave a lecture akin to this one some time ago, that in 1932 a Roman mosaic was found that goes back to the 1st or 2nd century AD of Leda and the Swan, and you see this imagery in these 4 octagons and the bigger octagon in the middle. And it represents 4 seasons: summer, spring, winter, and fall. And if we concentrate on winter here, then it turns out that overall, of course, there are 32 Solomon knots on this mosaic. Remember what I said about left-handed and right-handed varieties. 31 of them are all the same. Let's say they're right-handed. I don't know if anybody in the audience would like to find out in the winter quadrant here, or the winter octagon, I should say, perhaps using the clock face, the one that is out of place. Are there any takers for 9 o'clock? Well done. There you are. How did this happen? Out of 32, one day, maybe it was the apprentice, we'll never know, screwed up, and we got the other one. Or maybe it's intentional. But anyway, if you're a chemist, you say that this was delivered with a so-called 94% enantiomeric excess by the... So let me poke some more than fun skepticism at the whole art of crystal engineering. I mean, there are journals now in crystal engineering, but I really don't believe in it. And I tend to follow the words of John Maddox, one-time editor of Nature. One of the continuing scandals in the physical sciences is that it remains in general impossible to predict the structure of even the simplest crystalline solid from a knowledge of their chemical composition. That's how ignorant we are. So these Solomon knots, as I say, are everywhere. If we had 40,000 Borromean rings as hits, you'll get close on 700,000 Solomon knots. So back with knots galore. Just a little interlude here. I just want to point out that this one has just graced Nature Chemistry this month. And here you can see it picked out, you can read about it there. But why I'm proud about this is that David Lee was one of my early graduate students when I was in Sheffield in England. He's now a professor at Edinburgh University, shortly to move to Manchester, and he's prepared this 160 atom long pentafoil knot and one-step reaction from 10 organic building blocks and 5 iron 2 cations. So there you see it in there. So let's leave the Borromean rings and the Solomon knots and go to 2 catenanes, because this is where I sort of transfer to what might this be useful for. So here's the basis for building a switch that is bistable. The components that you see here are in green, tetrathiophylvaline, or TTF for short. In red, dioxynaphthalene, for short, DNP. And then this compound here is very happy to give up 2 electrons, become a dication, as we call it, to become TTF2+. And one of our molecules in trade, which I'll define on the next slide structurally, is the little blue box here, and it carries 4 positive charges. And the green above everything else loves to go inside. It's the first choice. This will never happen. Coulomb tells you, the physicist would tell you, no way are 2 positive charges going to sit inside 4. So if we switch off the binding between the green by making it this brown color, we have to go to the second choice, the red one going inside. And if you constitute the molecule in a catenane, you have this ring here with the green and the red. The green can be inside, and remember this is what we would expect because it loves more to be inside than the red. Or the red, in some instances, could be inside. And this turns out up here to be the major form that you find in solution, and it's how it crystallizes. You can see the green form inside the blue box, the red having to sit on the outside. Here is what we call a space-filling representation of the same. The green is inside the blue, and the red is outside. So we showed that you could take this compound, which turns out to be beautiful emerald green. The interactions here are such that it shows this green color in the visible spectrum. Or you can convert it by taking the electrons out of the green component, using this oxidant, to a blushing purple. And this is reversible. You can use ascorbic acid. If you don't like using chemicals, you can do it electrochemically. That is, with electricity. And going to the cartoons, this is the basis, effectively, for the switch. As you take the electron out and create the positive charge, the green goes outside and the red goes inside. And so this was the basis for a collaboration with physical chemist, physicist Jim Heath when I was at UCLA. Jim is now at Caltech, and postdoctoral scholar Pat Collier is now at one of the national laboratories. The name is just escaping me. And what Pat did was to prepare a smooth silicon substrate and by photolithography pattern this parallel polycrystalline silicon electrode onto the surface. And I will tell you about this technique. We'll just call it the LB technique for now, to deposit just one monolayer, one single molecule in a layer on top of this electrode. And then to evaporate on top of that titanium aluminium electrode to give us a crossbar. And the sandwich could then be subjected, if we look at one junction, to an electrical current, and the greens which are inside come outside and the reds go inside. And this is the basis then for a molecular switch. another view of it that shows the important part that the supporting counter-ions play. Remember, these are carrying 4 positive charges, so everyone has to have 4 negative charges. So we arranged that they had long hydrocarbon tails, and the reason for this was to use this oil to protect the switching gear while we were fabricating this molecular switch tunnel junction, or MSTJ for short. The switching mechanism is the same as the one that I've shown you already in the movie. We start off with the green inside. It gets positively charged in the device, and so it comes outside, and the red goes inside. So we start here, and at this stage, we have the red inside and the green outside. They are isomers. They carry the same charge. They are the same number of atoms, and so on. And this one then makes its way back slowly to that one. And it constitutes this the open form of the switch, and this the closed form. This one turns out to be the less conducting in the layer of monomers of molecules, and this one the more conducting of the two. This is the more stable state, and this is the less stable state. Now, there was one disadvantage to that first generation of switchable molecules, and that was the so-called on-off rate, the difference between the current that went through when the red was inside and the current that went through when the green was inside was only about 2 to 1. And so Jim and I argued in a brainstorming session one day that if we went from this catenane to the ritaxane, this, remember, it's the one that's stretched out with a dumbbell, then we might be able to just, it seemed intuitively, increase this so-called on-off ratio. But at the same time, we decided to make this molecule in its own right amphiphilic. So we gave it an oily end and a watery end. We still have the same addressable green and red sites, and we still have the same mechanism. But now we have movement between the bottom polysilicon electrode and the titanium aluminium electrode. Now, of course, there are actually thousands of molecules at each of these junctions. I'm only showing you one. And they're not straight. They're very, very crooked. But this is the best way of getting the idea across to you. So now this is the fabrication process involving the chemical synthesis. So you can see how you bring the components of the green and the red together. Put on the watery component and join them up, and then use the green component to template the blue component as a ring around it. There is the electrons being taken out of the green component, so that at that stage you have the more conducting, and now you have the less conducting form of the switch. How do we get these as single molecules into this monolayer? This is this LB technique that is coming up. But first of all, this is the work that was done at Caltech, making the chip that is now going to have the molecules transferred to it. It's been put under water in a so-called Langmuir trough, and the molecules are being compressed to the point where they line up almost like soldiers. And so that when you lift out the chip, quite miraculously, you get this monolayer, one molecule thick layer of molecules distributed on the chip. And you could now end the process with a further hard type of fabrication to give wires that are at right angles to the ones that the Langmuir-Blodgett technique was used to put the molecules on. So this would be a 4x4 crossbar device. And very simply, it's the basis for a 16-bit memory device, because if we now apply voltage to wires 1 and 3 here, and also voltage to wire 2 here, all the others grounded, then we will switch the molecules at the junctions there and there to the on state. They will become more conducting. And they will keep that information. And if we want to read out the fact that this molecule or set of molecules are in the on state, then we can do this in the read part of the device using an ammeter to show the increased current at this particular junction involving these two wires. It's pretty complicated, but that's as simple as I can put it. We moved from this 4 times 4, 16, up to a 36. That is a 6.6 cross-point structure. Not all the bits were functional, so something like, 11 malfunctioned. It left us with 25, and we used 16 of those to put in, using the binary code, these ones and zeros for these particular numbers picked out in green. 1 is the on or closed state of the switch, where you have current. The 0 is the off state of the switch, where we're on the baseline here with the black line. And this was taken up as far as a 160 kilobit molecular random access memory using this particular rotaxane that you can see here with the watery end and the oily end, the green component there where the blue ring prefers to sit, and the red component. So it had 400 wires by 400, giving us a total of 160,000 junctions, a 60 kilobit situation. And here you can see 250, 100 junctions out of these. This was a small amount of the circuit that was tested. And before I show you the outcome of the test, I just want to point out that the size of this device is represented by this imagery here. And in order to put it in context, this is an ethanolic solution with white blood cells suspended on top. So this little device here, with its 60 kilobytes of memory possible in there, is smaller in diameter than the diameter of a white blood cell. And so Jim tested 128 bits. Here you can see the test, and was pretty discriminating. Anything below this 1.5 threshold was abandoned as not being a good device. So it actually meant that 3/4 of what had been built was not functioning. It left 27% of good switches, and that 27% was used to using the so-called ASCII 2 code to print out California Institute of Technology at a density of 10 to the 11 bits per square centimeter. So that is a lot of bits, particularly if you write them out like that. So now we have a situation that we have a semiconductor Rohnbach comparison where the density of the memory is about a decade ahead of where we expect it to be if we use the technology of today. Now a short segue into the problem of cancer. In this country, 750,000 of men and women will be diagnosed with cancer this year. And the current treatment that's on the market is to use these hard drugs. I give 2 examples here. The problem with them is that they destroy healthy tissue as well as the tumor tissue, and the side effects, as I well know from personal experience, are quite excruciating to behold. So our thought is, could we use a different type of delivery system to take these rather oily hydrophobic drugs into biological tissue? So a relatively new approach that's being used in this area is to make the drug molecules smarter by encasing them in a situation where the anti-tumor drugs could be delivered selectively within a delivery vehicle, and therefore reduce their exposure to healthy tissue and also reduce the amount of drug that is delivered, maybe by many orders of magnitude, and make it therefore very much safer. And so again, if I can just use some imagery in a minute. We have these mechanically interlocked molecules now associated with silicon nanoparticles that are riddled with cavities that are cylindrical in nature. The actual nanoparticles are about 100 nanometers in diameter, and the cylindrical cavities about 2 nanometers in their diameter. Just the right sort of size in which to put a classical hard anti-cancer drug. And here again is a movie to show you the idea that you have many of these channels into which you can encase the drugs. In an ideal situation, you could have markers on the side of the nanoparticle to induce the nanoparticle to go inside the disease cell only, and then signal the opening of these gates, as we call them, to allow the drug to come out, and then it would be bad news to the cancer cell. So these are what the mesoporous nanoparticles look like. If you look at them by electron microscopy, about 100 nanometers in diameter, with these 2 nanometer cylindrical cavities all the way through. And there are various different varieties with hollow centers and with magnetic cores as well. Here's another way of looking at the situation and how the machinery works on the surface to allow the drugs to be encapsulated, held within, and then released on demand. And this again is a decade-long activity that is going on, started about 2001 in collaboration with one of my ex-colleagues at UCLA, and we're making good progress. Now, a challenge, am I all right on time? Yes. That remains, and it really is a grand challenge. It's the sort of challenge that the Wright brothers, amongst others, took on just over a century ago to bring about manned flight. We can make these artificial molecular switches. They're a dime a dozen. What we can't do with any real aplomb yet is to make artificial molecular machines. They are few and far between. Yet we are functioning as living beings just full of these biologically driven machines. The difference is that the machines need to perform work on their immediate environments. And we just brought out a review in Chemical Society Reviews. Again, it's topical. It's just come out on the 7th of January. I guess it's still to come out, but effectively it's online, where what we're trying to do is to point out to the people in the field that what we need to do is to think about assembling and controlling synergistically artificial molecular machines housed in highly interactive and robust architectural domains. And if we can do that, it will herald a game changer for chemical synthesis and a defining moment for molecular nanotechnology. So this is effectively one of the big intellectual challenges that all of us in the field are facing at this moment. Okay, so let's just back off from that just for a minute to something quite simple. Some very simple rings. These are rings that are made up, and they're given to us by nature, from starch. If you allow starch to interact with a certain microorganism, it will produce rings of glucose units that are shown here, these units that are 6 there, 7 here, and 8 there, in a circle. And they're called cyclodextrins. They're synthesized, as I said, by a bacterial enzyme. They've been well studied. And we stumbled across the fact quite recently that the one with 8 sugar units, which is bucket-shaped in itself, principally because of its symmetry, and what is attractive about it, it's produced in the ton scale from cornfields in nearby Illinois, beside Chicago. And it was serendipity that took us to something quite spectacular. So Ron Smaldon, himself a graduate of the University of Illinois at Champaign-Urbana in the south of the state, was one day trying to put these two organic molecules together inside this gamma cyclodextrin with 8 sugar units. And so he grew some crystals. You've heard about this game before. They went across the pond to St Andrews University, and we didn't see anything, or Sandra, Alex Slowen, didn't see anything reminiscent of this structure here at all. She found that it was a cuboidal type structure. 6 of the cyclodextrins had been used to form this cube, and this is extended in 3 dimensions throughout the extended structure of the compound. And we got this cryptic email from her. I see the cyclodextrin. I see 4 atoms of potassium weight. I see water, but no other guest molecule. So all of this had been, as it were, lost in the X-ray diffraction study. She only saw the cyclodextrin and the purple, which is the potassium ions. And these are held together just like cages, interconnected with each other. And this was quite an exciting discovery, quite serendipitous. And it's what I call Bob's your uncle chemistry. You take a spoonful of sugar, you take a pinch of salt, and you take a swig of alcohol, and Bob's your uncle. I don't know if you're familiar with this phrase. It's one that is much used in the Commonwealth countries, as it's called. It's a way of saying you're all set, you got it made, that's great, it's happened. And what's more, you can create this metal organic framework, they're called MOFs, in a context where you use food grade material. You can use food grade cyclodextrin. You replace the methanol, of course, with a source of ethanol, Everclear, from a nearby store. And you have your CD MOF composed entirely of food grade materials. And so this is important because these metal organic frameworks are now rather big in terms of commercial reality. BASF are putting out 40 tons a year based on metal organic frameworks made with petrochemical sources of building blocks. Our porous solid from cyclodextrins is the only one that is USP grade, made from USDA certified materials. And it's a food grade solution to, I think, many possible applications, because it's safe, it's non-toxin, it's very cheap, and it's Bob's your uncle chemistry. It's easy to make. Of course, you would think of going into the pharmaceutical industry with this right away, but I think there are other much more low-hanging fruits that you could go in search of in the food industry, in the personal care industry, or the home care industry. And so here, we're quite excited at the prospect of applications that would prevent or detect food spoilage, or the addition of flavors to foods. Application for personal care, different ways of delivering fluoride in toothpaste, deodorants, and so forth. And also in getting the atmosphere that we are living in, particularly if you're traveling a lot, as I am, in a jet plane. We want the air to be as good as possible, and so to be free of these diseases like asthma and so forth. So applications to home care. Right, so we're pretty excited by that situation, but I come back to my theme that all of this comes together because of the intellectual input from graduate students who are absolutely committed at the time. And Scott is in the audience. I want you to stand up, Scott, so everybody sees you. And Kirsten is in the audience, please. And Doug is in the audience. They're both UCLA graduates. Doug made the transition from California. It wasn't easy, was it, Doug, to Chicago in January of 2008. there's a story to be told there, but you survived and you now have a Northwestern degree. And they're all working here in the DC area. And they are the music makers. This is what they would say. We are the music makers, and we are the dreamers of dreams, wandering by lone sea breakers and sitting by desolate streams. World losers and world forsakers, on whom the pale moon gleams, yet we are the movers and shakers of the world forever, it seems. So really my story tonight is one where the most important thing has been the education of, I don't know, 300, 400, 500 graduate students and postdocs over a period of almost half a century now. It's given me a lot of pleasure, and we've made a lot of discoveries on the way. We might have a startup company later this year. I always say that we can only train good researchers on the basis of doing cutting-edge research. But finally, let me just leave you with some final thoughts of chemistry in a contemporary vein. To underline the fact that this is the youngest pursuit there is in science. If the atoms are the letters, and if the molecules are the words, and if the supermolecules are the phrases, then the language we call chemistry took less than half a century to make the revolutionary transition from molecules to supermolecules, on the back of having taken well over a century to make the painstaking journey from atoms to molecules. If we peg the growth of chemistry to the expected lifespan, let's say at least 70, of someone living in a developed country, then we're looking at no more than a 2-year-old child who's just starting to string a few words together. The chemist has still to learn how to construct sentences that adhere to some grammatical rules. That is, to introduce meaningful and helpful complexity at the simplest of levels into chemistry, and then acquire the skill set required to bridge in a logical fashion from sentence to sentence, and so produce coherent paragraphs that ultimately tell a story when they're merged together in the form of a complete work. It is at a crossroads with nanotechnology that we can recognize some of the most promising opportunities for chemists to express their creativity. First, we need to forsake simple systems for complex ones. The building blocks in chemical systems constructed from them need to become more intricate with respect to both structure and function. Dynamic chemical bonding needs to be harnessed across its entire energy spectrum, from the tiniest so-called van der Waals forces to thermodynamically reversible covalent bonding interactions. Second, we need to forsake the solid and solution states for surfaces and interfaces. Chemical systems need to become bigger and to express multivalency and cooperativity with feedback. In essence, we need to forsake embracing routine projects that we know will yield results and lead to answers that are largely expected, so as to face challenges that are function-oriented and applications-driven, requiring the design of integrated systems whose complexity is such that perhaps unexpected emergent behavior is likely to be the result. The time has come to design and craft a systems chemistry in which processes, including chemical reactions, are compartmentalized in a highly interconnected and talkative manner so that they can be orchestrated in tune in an orderly and rhythmic fashion by the hundreds and thousands in space and time. So I hope I've left you with not only the beauty, but the promise of chemistry and molecular nanotechnology. It is huge. We are only just 2 years old on the human timescale. There's a lot still to be done. Thank you again for the invitation to come.
Thank you very much, Professor Stoddart, for a very illuminating and fascinating lecture. We have time for a few more questions. Please stand up, speak loudly, because the auditorium has not very good acoustics. Yes?
Are most of the structures determined by X-ray crystallography?
Sorry, most of the structures?
You determine most of the structures by
Oh.
crystallography.
Only in part. At least two of the graduate students that are over on this other side are experts in nuclear magnetic resonance spectroscopy, which I did not discuss tonight, but that has been used both in solution and the solid state as a major form of characterization, along with mass spectrometry and many other techniques. So it's just that the imagery that one gets from X-ray diffraction studies is easier to portray. Yes?
A short technical question and maybe more technical question. The short technical question has to do with the linear logic technique that you use to do the relaxanes on the substrate. You say that when you start applying the pressure, surface pressure, the molecules align themselves. Does it happen because one end is hydrophilic and one end is hydrophobic, or does it happen all the time in linear logic talks, or?
It's probably not wise for me to say that it will happen all the time. And it's not wise for me to say that they would have to be amphiphilic, i.e. have a hydrophobic or a plus a hydrophilic end. Certainly an amphiphilic molecule will stand a much better chance if one is carrying out this process on water. But I should just parenthetically say that there are now people doing Langmuir-Blodgett studies on mercury and so on and so forth, so it would be dangerous to generalize. But basically you want to use some kind of polar aspect to the molecule to be able to help you in this alignment process. But again, it is like crystallography, because it's beginning to be, if you like, crystallography in 2 dimensions. It is more of an art than it is a science, I would say.
And the magnitude question has to do with the effect on the previous slide. Chemistry has to take a function-oriented direction, you said, I think.
Well, I think...
You're building these micro-machine precursors, I guess. Did you ever have anybody come to you and say, I have this application, can you design a molecule for it? I mean, drug delivery is an example, but drug delivery, as far as I know, is a prevalent example. Does somebody come up with an application that made you go, I never thought of that?
Yes, that does happen, and we do respond to it. I think there are many, many ways by which our science can be driven forward, and we have to be very, very open about the different stimuli that would be used to create a new avenue to research. I did very much want to put in that last story about Bob's Your Uncle chemistry, because this was something that was not predicted. We were trying to do something else, and as has often happened in the course of scientific discovery, we find something that we're very excited about. And as I say, we're in the point of starting a startup company based on that very simple observation. Take a spoonful of sugar, a pinch of salt, and a swig of alcohol, and boom, you've got a new compound. And it's cheap and it's ready, it's edible, it's green, it's everything that you would want it to be. Yes, we very often have somebody comment about function and try to respond to it. I think if I can use your question to make the point, that one slide I put up speculating about the transition from artificial molecular machine switches to artificial molecular machines. Yes, a lot of people have actually come to the chemical community and been quite critical about our naming our switches as machines. You know, they'll point out, you know, go and read the definition of a machine. You have to do some work on the environment. You're not doing any work. You're just switching from one point to the other, and it's going back and forth. What you've got to do now is to take that and couple it to something that creates work somewhere in the environment. And so I think at an intellectual level, that is a very good example of what you're talking about. It's not an application driven one yet, but it's an intellectually driven one of great importance.
Let's say,
For a sense of perspective, I just wondered if you might comment on the comparison of these brilliant examples of human endeavor with what nature has done through Darwinian selection over 4 billion years in developing nanomachines that do many of the things that you've described here.
Sure. Indisputably, nature has, of course, used time and effectively well-defined, which has probably changed over the many millions of years, environment to fashion molecular machinery on a exquisite scale. This has led to the life forms that we're all part of and appreciate. My argument, though, has always been that what has been possible in nature is in principle possible to create without going to natural systems. And so we have really posed for most of the work in my research group the problem in the context of let's try to build things that imitate what we know happens in nature using abiotic type building blocks. And progress is so far slow. And you know, I often, again, if I may return to the analogy with flight, and make the comparison that the birds and the bees and the bats have been carrying out that function for millions and millions, trillions of years. We've only been at it really in a successful way for 50 or 60 years. So as human beings, we can take functions or structures, I think, and create our own artificial context, because coming back to the birds and the bees and comparing them with the jetliners and rockets and helicopters of today, there are some similarities, but there are a lot of differences in the design and the operation of the two.
the gentleman next.
Yeah, on a lighter note, you mentioned using iron too to make a circular molecule. Did you call it a Ferris wheel?
I think actually that word has been used already in a slightly different context a few years ago by some other authors that put iron into a large compound. It has been used, yeah.
Yeah, you started mentioning the Platonic solids.
Yes.
You didn't mention the Archimedean solids, which are semi-regular. I have several classes of nearly regular solids that I believe many of them would be useful in the kinds of things you're talking about. How do I get them out? How do I get them? Where would I publish them? Where would I talk about them?
It's always difficult. It's always difficult to give anybody any advice on where to publish anything, because that again is another subject of its own, which has very little predictability to it. But you know, there's many ways.
Perhaps there's a place I can talk about them.
Yeah, sure. I think increasingly we should just go onto the internet and talk about things and let it happen that way, rather than you know, have to go through some of these hoops. But I did mention one Archimedean solid, I think, briefly in my talk. But yes, I realize that there's much more than Platonic solids. Yep.
Looking at your example of the stretching of the molecule by using a hydrophobic and a hydrophilic end, it occurred to me that you must have had some thoughts about if you're going to look for biological applications or physiological applications which involve drug delivery. You must have had some experiments or pre-thoughts about how to use lipids in the construct of these nanosystems, because they undergo conformational changes under circumstances which are easy to tweak
of molecules with very small energies, less than eV. I wondered if your group is engaged in any of those.
We're not as such. I mean, we do think about these things and we follow the literature as closely as time will permit in areas where people use biologically constructed building blocks to carry out nanofabrication and so forth. It's just not been one of our hot pursuits. In making that comment, I'm not being degrading in any way towards that activity. I think it is incredibly important. It's just that I think there is room for other approaches. Yeah.
It's time for two more questions. The gentleman in the back.
Two more physical questions, Professor. One of the problems with doing standard computer chips as we miniaturize them is how do you make the connections?
Yes.
The same question on your arrays that you have built. How do you make those essentially electrical connections so you can read or check what's in there? And the second question would be, is there any usage of radioactive elements in doing what you're doing, or would that be too destructive of the more organic compound?
I'll take your second question first of all. We've certainly not delved into the use of radioactive compounds in any of our work. I don't rule that out. Until very recently, and by that I mean the last 18 months, we had not contemplated using chemicals with free electrons that are called radicals. And now this has suddenly become a major part of our research effort. So I don't think you ever close doors. The interconnects problem is a very good one that you raise. We are certainly not the experts in this collaboration. This work was carried out by my collaborator, Jim Heath at Caltech. And basically, I can only just describe it in words where they are using a whole form of multiplexing in order to be able to address and to write and to read out from these many wires that are part of this device. So that is another science in itself, the multiplexing that has to go on in the background to be able to monitor the information that is read into the device and written out from it.
Last question, sir.
You mentioned when speaking of the Borromean rings that the reaction was bidirectional. It was constructing and deconstructing at the same time. I'm wondering how you actually extracted the final product. Was there something that drove it in one direction, or did it precipitate out, or were you...
Yeah, it crystallizes out, and this is the important aspect to it. It's not something that you can predict, but again, it was a choice of solvents that gave us in particular the Borromean rings. Another choice of solvents gave us two rings of the Borromean structure, but totally and doubly interlocked, as it turned out to be the Solomon knot. The transition from the solution phase to the solid phase is usually accompanied by a kinetic situation. That is, the thermodynamics are arrested as you make that transition, and so that allows you to get your hands on the material that we were able to get our hands on. Crystallization is important.